Okay, I did post the next project. It's a state machine project. There's not that much code involved if you put down the right code. And then the other thing to note about this project, I made it due, I think, a week from Thursday at 11. Because the Monday, Wednesday, Friday wasn't working for me with checking on projects. I've got 4 classes that day. So I just made it Thursday when I don't have any classes. It's at 11, so it doesn't interfere with my lunchtime. So make sure you get in there before my lunch because I'm going to be signing them late. So I believe we have our next exam in here on Monday. Is that correct? And so Friday we'll use as a review. I do want to kind of finish up a topic in chapter 6. It's on matrices and graphics. So I'll look at it actually hooking up the little LCD display. He's provided a library of routines to interface to that display. But he doesn't actually have any projects using it until I think chapter 8. So we won't actually start using it until after the exam. But we'll go through actually how to clear the display, how to set pixels, how to clear pixels in the display. But usually when you're working with graphics, a screen, you need to work with 2-dimensional data structures. We can have higher dimensional arrays in C. This is how you would declare an array with 2 rows and 3 columns. It could be higher dimension. There are a couple of different ways actually to define 2-dimensional data structures in C. This is a standard 2-dimensional array. You can also do it having arrays of pointers. But conceptually, you can view this as laid out like this. The first element is the 0, 0 element, and then the first index is the row index, and then A0, 1, A1, 1, A0, 2, A1, 2. Conceptually, that's actually how we think of a matrix as this 2-dimensional data structure. But memory, of course, is a linear array of bytes. The 2-dimensional array is laid out in memory. And again, for these data structures, it's helpful at times to know how exactly the data structure is laid out in memory. We can treat a 2-dimensional array or even a multi-dimensional array as a single-dimensional array, a linear array. In memory, and I'm just going to make up an address here for the first element. The array is laid out. The first element in the matrix is the first element in the array, and that's fortunate. And that's easy, right? I mean, I guess they could have laid it out so that the last element was first. And because this is an int array, and all the elements are 4 bytes in length, the next element, and then here's where the choice comes in. You can lay it out either in what's called row order, row by row by row, or column order, right? And C, it's laid out in row order. The next element is actually the 0, 1 element, and then the 0, 2. And then so I realize I'm getting far down here on the board. You're going to have to crane your necks. And that's just the way the designers of the C language decided to lay out two-dimensional arrays. Is the first row, followed by the second row, followed by the third row. Not all languages follow this same convention. Fortran actually lays out matrices in column order. It's the first column, and right below that is the second column, then the third column. Actually, MATLAB, it's been around for a long time, was originally written in Fortran. It's been since mainly written in C now, and ported to C. But in MATLAB, if you actually print out a matrix as an array, and you can do that pretty easily, you'll see that the matrices are actually stored in column order, corresponding to the way Fortran originally laid out matrices. Okay. So what this means, this looks very much like an array of length 6. This is how an array of length 6 would be laid out in memory, an int array, and you can access the elements just like they were laid out that way. The variable a is a pointer to the first element. And so star a is the same as a 0, 0. And you can use either notation, okay, star a or a 0, 0. Again, that's dereference. A is the address. The star or asterisk dereferences the address and gets the value. So you can use that on either side of an equal sign. Simply star a plus 1 is the same as, now again, a plus 1 here, when you're working in C, that's not 1 byte above the address. That wouldn't be the address 1001, because the compiler knows that A is an array of ints. 1000 plus 1, there would actually be the address 1004. It's incrementing to the next element in the array. And then similarly, we can actually access the last element as a plus 5. And that would be the last element in the array. Okay. So you have, when you're writing programs that are working with these two-dimensional arrays, you can either access them as two-dimensional arrays, but sometimes it's faster or more convenient. We'll see this a little later today when we're working with the graphics array. It's more convenient to actually treat it as one long multi-dimensional, or one long array, single-dimensional array. More generally, if A is of dimension A with m rows and n columns, then star of A plus I times n plus j is the same as A I j. Notice here, to actually compute the offset, you really just need to know the number of columns, right? The number of elements that are in a row. So you take the row offset times the number of elements in a column, which is capital N, and then add the column offset to get the right address of that element in the array. Okay, so let's talk about this little LCD display that you have in your kit. It's from an old cell phone, but they produced millions of these little display elements for the cell phone. And then I don't know, the cell phone wasn't very popular or something. These things are still, you can get these little LCD displays for these things. They're really inexpensive. I think 50 cents for these little displays. So they're inexpensive, they're relatively easy to interface to a microcontroller. It's a 48 by 84 pixel. So 48 rows, 84 columns, black and white LCD display. Each pixel is mapped to a bit in memory. And if the bit is a 0, that display element is off. And if it's a 1, that little display element is on. Now, with most displays, you don't actually work directly on what's called the video memory. Instead, you work on what's called the video buffer. It's just an area of memory that is laid out just like this has the same number of bytes as the video memory, but you update the video buffer, do all your operations on the video buffer, and then you transfer the video buffer to the video memory to update the display all at once. So you have whatever on the display, and then you're working with the video buffer, producing actually creating the next display that you then write out to the video memory. And that's the way this thing works. Now again, our little display here is a black and white display. Okay. So there are only 2 settings, either on or off, just like on a fax or a printer, a black and white printer. There are what are known as monochrome displays, okay, or gray level displays, where you can show images with different levels of gray. Typically those, you have a byte corresponding to each pixel. And so you could have 256 different levels of gray for each pixel, and what we usually call a black and white image. It's not really a black and white image on a computer screen, but it's a monochrome image. And so that's a little different. And then color images for each pixel, you typically have 3 bytes. Each pixel is mapped to 3 bytes of memory, 1 for red, 1 for green, and 1 for blue. And so you have 24 bits actually for each pixel. You get 256 different levels of red, 256 levels of green, and 256 different levels of blue. That, combine, I guess these aren't really the primary colors, but they can be combined to create all the possible colors you see on your computer monitor. But we're starting with a much simpler case. In some sense, it's not quite as easy working with a black and white display where every pixel is mapped to a bit as it is with a gray level display where every pixel is mapped to a byte. Because here we actually have to get down to the individual bits in the memory locations. And we've seen that we have to do these masking operations to set and clear bits. It's actually a little easier to access bytes. So with this particular display though, in order to work with it, you really have to understand how the video memory is laid out in order to set or clear a particular pixel. So there's 4,032 pixels. That corresponds to the certain number of bits. So a byte in memory would actually be mapped to 8 different pixels on the display. So 48 by 84 divided by 8. That means it takes up, the video memory is actually 504 bytes in length. And then here's how we're going to conceptually think about, these are the columns of our display. The 0, 0 element is in the upper left-hand corner of the display. We've got to figure out how the pixels are actually mapped to our memory array. And then this would all go to 83. And then these are the rows. And then we've got 47 rows. So the 0, 0 pixel or our home pixel is in the upper left. It's not true for all displays. In some displays, the home pixel or the 0, 0 pixel is in the lower right. Okay, it just depends on the display manufacturer. But here, the 0, 0 position is in the upper left. Okay, so the pixels are laid out like this. The memory layout's a little bit unusual. The first, make it a little wider. The first byte, or the 0th byte, actually is the first 7 pixels. Okay. The next byte in memory, remember, this is all laid out in memory as just one long array. I'm going to show it in 2 dimensions, just like I showed the matrix here in 2 dimensions, laid out in a table format. Even though in memory it's just one element right after the other. So the next byte, this is the first 8 pixels then in column 1. And then after that would be the 8 pixels in column 3. Until you get to the 83rd byte is the first 8 pixels in the 83rd column. The 84th byte would actually be then rows, pixels 8 through 15. It seems a little bit unusual as it's laid out this way, but actually, so we can do what are known as bit-mapped graphics, setting individual pixels. We can also write ASCII strings to the display. But with the ASCII strings, we're limited to actually 6 rows of ASCII text. A row of ASCII text takes up 8 pixels. Actually, each character is an 8 by 8 pixel block. Okay, so he's got a picture in their textbook, but for example, if I laid out an 8 by 8 frame here, and that's 4 by 4, but you get the idea. Well, I'll double it. Then, the letter B would consist of maybe something like this, right? Hopefully a little better than this. That looks more like an 8, but it would be laid out. Again, you've got a nicer picture in the textbook of what the letter B would look like. And then so we can spell out, the characters are nothing more than turning on individual pixels in this bitmap array. And so we can write out ASCII strings, but that's really just turning on individual bits in the video memory. So it's laid out kind of like this, but because it makes it a little easier to do the character graphics. The 85th bit would the 85th byte in memory would correspond to this set of pixels, 8 through 15 in the second column. This would be then byte 167. And then in the last row, that would be 420. So, and it would actually be 5 times 84. This is, got 84 bytes in the first row, 84 bytes in the second row, 84 in the third. So this would be 420, and then 84 bytes here, which would make this actually byte 503. Okay, 504 bytes in our array, but they're indexed 0 through 503. So this is the memory layout of or the byte layout of our video buffer. Now, what we want to be able to do is actually, maybe the basic things that we want to do are set an individual pixel or clear an individual pixel. In order to do that, it would be convenient to take our I and J pixel indexes, the row and column. We have to figure out what byte index in memory they map to. So, like, for example, I15J0 needs to map to memory index 84. So does row 8, column 0 maps to the same memory address, but it maps to a different pixel or a different bit in that byte. Right? So in order to set and clear pixels, we need a way to actually get the index from the I and J pixel value. So convert pixel I, J, row and column, index to byte index n. And of course, I can go from what I say 0 to 48, 47, and J can go from 0 to 83. Of course, N goes from 0 to 503. So I'm going to give you a few minutes to actually think about this and see if you can come up with a formula to find N in terms of I and J. Well, here's one way to do it, and there are several. But if you'll notice, you know, the I values 0 to 7 all map to my first row here, and then my first row in memory. Thinking of memory as this two-dimensional data structure, and then pixel rows 8 through 15 map to the second row. The way to get that mapping is actually to divide I by 8 using integer division. So we could write this as I divided by 8. So 0 through 7 here, if I is 0 through 7, this will map to 0. And then if it's 8 through 15, that will 8 through 15 would map to 1. So 8 through 15 divided by 8 is integer division. Throwing away the remainder, 8 through 15 would map to 1. And then similarly 16 through what's 23 would map to 3. But now I actually need to multiply that by 84. Because again, the 8 through 15 divided by 8, that's 1. I need to add 84 to get into the second row. And then the J is just the offset. At least I think that works. What I tend to do is actually make a little table to check to see if that looks right. So certainly 0, 0 maps to byte 0. 1, 0, where does that map? What memory index does that map to? Now 1 divided by 8, integer division, is 0. So this looks a little odd. It maps to byte 0 also. But remember, the first 7 pixels are all in byte, I'm sorry, the first 8 pixels, 0 through 7, are all in byte 0. So, you know, for I between 0 and 7 here, they should all map to the same value of n. Well, let's take 0 and 1. Where does that map to? Well, that's going to map to byte 1, right? Which is correct. The 0, 1 element is in byte 1. Okay. And then let's take maybe, I don't know, 15, 1. According to that, according to this picture, 15, 1 should be this bit in byte 85. 15 divided by 8 is 1 remainder 7, right? So with integer division, we throw away the 7. So that would be 84 plus my J, which is 85. Okay, so that looks right as well. We can test the very last, what I say, this is 47, 0 to 47. We can test the last element here, 47, 83. 47, 83. 47 divided by 8 is actually 6 remainder 7. Oh, I'm sorry, 5 remainder 7. Right? So 5 times 84, that's actually the 420 here. And then plus the 83 is the 503. So it looks like, I'm pretty sure this is correct. The other way to do this, if the integer division bothers you, is this is the same. This is how he has it written in the textbook. dividing by 2 is equivalent to just a right shift by 1 bit. So that's not right. So dividing by 8 is just right shifting 3 times. Right shift once, I divide by 2. Right shift again, I divide by 4. Right shift again 3 times. That's equivalent to 8. So I'm essentially just throwing away the lower bits here. And I. Questions about this? The other thing we need is to find the bit within the byte. The formula there is actually a little simpler, and you might be able to guess at that. We see here we threw away 3 bits of I. They've got to be useful for something. They're useful, or that remainder is actually useful for finding the bit position within the byte. Now I should mention, because it's not necessarily the case, that bit 0 in the byte is at the top here. It could, depending on the display manufacturer, it could be bit 0 to be bit 7. But bit 0 is there in the top position. So to find the bit, it's just the remainder after dividing by 8. So, and we can check that. So here the remainder is 0. 1 divided by 8 is 0, remainder 1. So the 0, 0 element would be in bit 0 position of memory element 0. This is B0. The 0, 1, I'm sorry, the 1, 0, second row, first column should map to B1 in memory element 0. This will map into the 0, 1, first row, second column, maps into the 1, 1 position. I'm sorry, using I, maps into the 1, 0, memory element 1, bit 0 position. So that maps into memory element 1, bit 0 position, the 0, 1 element. That looks right. Where should the 15, 1 element map into? Should map into bit 85, memory location 85. We've already got that, into bit 7. So 15 remainder, 15 divided by 8, the remainder is 7. And similarly here, 47 divided by 8, the remainder is also 7. So these are the bit positions. Now really what we need to set individual bits is not the bit position, but really the corresponding mask value, right? Which we've been using throughout this semester to set and clear particular bits. How do you get the mask? What's the formula for getting the mask value from B? Okay, think of it this way: we want to set bit 0. What would be the corresponding mask value that we have to use? If we want to either set or clear bit 0, what's our mask value in a register, just like we've been doing? Remember, you got to put a 1 in that position. The mask value, if we want to mess around with bit 0, we got to have a 1 there, 0, 0s everywhere else, right? So what's that value? That's 1. If we want to set bit 1, what's that value? 2. If we want to set bit 3, what's that value? 4. We want to set bit 4. What's that value? I'm lost. 8, right? To get from the bit values here that go from 0 to 7, all we need to do is actually, well, there's a couple different ways to do that. I guess you could take 2 to this power. That would do it, right? 2 to the 0 is 1, 2 to the 1 is 2, and so on and so forth. But I think this is probably a simpler way. Actually, write in terms of B, or more directly, we don't really need B. Because what we really need is the mask value. So here's my B value. What's 1 shifted left, 0 positions? That's still 1. So that's 0x, 0, 1. 1 shifted left, 1 bit. What do I get? That's 2. 0x, 0, 2. Here, this is still 0x, 0, 1. What's 1 shifted left? 7 bits. Well, that'd be decimal 128, but hexadecimal, it's 80, right? I've shifted the 1 7 positions to the left. That's all the way to the most significant bit. So that upper nibble would be 1, 0, 0, 0, which is 8, and then the lower nibble would be 0. So again, these are already predefined for you as bit 0 through bit 7. But this is how we would get the mask for, it doesn't depend on J at all. It doesn't depend on the column index. It only depends on the row index. So this takes some head scratching to get these formulas right. When you're faced with a problem like this, or where things are actually laid out in memory, or maybe it's completely up to the designer that the bytes could have been laid out, like this, corresponding to the different pixels and memory. Now, again, when we get this video buffer set up the way we want it, we transfer it to the video display. Okay, it would be nice working with this video memory. We don't really want to access, the array directly. It would be nice to have some helper functions to do these conversions for us. We could certainly use the formulas anytime that we wanted to. That are there on the board to get the memory index and to get the mask. But it would be nice to have some helper functions. I would probably have as constants number of rows, what do you say, 48? And then the number of columns is 84. Okay. So we want the function, maybe call it get index, where we pass it the I and J values, and it returns the byte offset, this value of n. So here's the formula. We really just need to, so it's a one-line function, but it's useful. What is it? I, and then times, here I would use my hard-coded value, and then plus J. Okay. I would write a get mask function. Now, the int here can't be a uint8. Why can't it be a uint8 type? What's the maximum value you can have in uint8? uint8, 8 bits can go from unsigned, can go from what? 0 to 255, right? How many elements do we have in our array? 504. So a uint8 type is not large enough to hold it. We could use a uint16, but I would probably just use an int here. Now for the mask, though, those are all 8-bit values, and we want them to be 8-bit values. So for the get mask, return what I have over there. It was just one shifted left. And that was, what was it? I remainder 8. That's going to return my mask value. Doesn't depend on J at all. So could you write it so it only took I? Yeah, I think it's actually nicer so that it's written just like the get index and takes the same arguments, even though J isn't even used. Okay, I call get index to get the index. I call mask to get the mask value that I want to use. Now, the utility functions what I would probably we want some way to actually clear the entire array, set it all to zeros. That would correspond to clearing the display. So let's have a clear screen. And here what I would pass is our array is a uint8 type. And I'll pass a pointer to the first element. And actually, I don't think we need anything else. This would pass a pointer to the first element of, we'll call it screen. And then here, we don't have to clear the individual bits. We can just set the entire byte to 0. We don't have to step through all. I mean, you could set each individual bit, but that would be way too slow. There's no need to do that. So here, you could do this like this, and I is to 0, I less than 504, I plus plus, and then it would be screen plus I is equal to 0. And you could write this like that if you wanted to. Treat it like an array with 504 elements. That's just going to set every byte to 0. So, typically what you would do is update your video buffer, get whatever image you want on there, transfer it to video memory. Then you would clear the video buffer and start on your next image. And then clear screen would do this. Now at the fundamental level, we probably want to be able to set and clear individual bits. And then after that, you might want to write routines to draw lines or circles or rectangles, all kinds of little shapes, different offsets. But the fundamental routines we want are how to set a pixel and clear a pixel. And then here again, we'll take a pointer to our screen. And again, we started out talking about two-dimensional arrays, and you could certainly treat this as a two-dimensional object. It's actually, I think, a little easier to treat it as just an array of 504 elements, int I, int j. Okay. And you could probably write this in one line, but what we need is we need the byte index. How are we going to get that? We've got a helper function to do that. Right? That's why we wrote these two things. So we can say int index equals get index I and j, and then I need my mask uint 8t mask is get mask of I and j. There was no reason for me not to spell mask with an A, but I was just trying to make it the same length as get index. So I've got the index and the mask. And we could do it like this, screen. This is the actual byte that I want to affect, right? At this index, how do I set that bit? Set the corresponding bit. That's where the mask comes in. Now, if I set it equal to mask, is that what I want to do? Why not? Yeah, if I set it equal to mask, that's going to set that bit, but it's going to clear the other 7 bits in that byte. I don't really want to affect those other 7 bits. It's just like writing a bit in a control register. I want to just set the bit at that mask location. Each of these masks corresponds to one of the 7 bits. I want to set that without affecting any of the other bits. So the way to do that is actually read what's there and then OR that with my mask. Because my mask has a 1 in 1 bit position and zeros everywhere else. So if I OR with a 0, it doesn't change. But if I OR with a 1, it changes. So that will set that 1 bit. Now we've been writing this like this, just the shorthand notation, or equal mask, right? But that's just shorthand notation for that. Means read the value that's there, read the byte that's there, or that with the mask, and then write it back. Okay. This is actually equivalent to, yet the other way I could do this, screen plus index. Or equal mask would be yet another way to do that equivalently. And but this is my set pixel function, right? This would set an individual bit in one of these 504 bytes. Okay. Now, what would clear pixel look like? So I'm going to have these same two lines, right? But how do I clear a bit instead of setting a bit? Then it's anding, right? And equal. Do I and and equal with mask? No, with the complement of mask, the bit complement, right? Because the complement of mask would have a 0 in that one bit position and 1s everywhere else. Ending with a 0 would clear that bit, leave all the other bits unchanged. So at least we've got the start of a little graphics library for this display. We can set individual pixels, clear individual pixels, clear the whole display. We still need to figure out how to transfer this memory out to the little LCD display. But that pretty much wraps up all I want to cover in this chapter. So we'll review on Friday.